Hi, this is Sayed Faraz Ashraf and I am making this video for assignment 2, and the method I have selected is Euler's method. Well, differential equation that we have been through could be solved with this method. The problem with this is that there are exceptions rather than the rule. The vast majority of first order differential equation can't be solved. So in order to let you something about solving first order differential equations, I had to restrict ourselves down to the fairly restrictive cases of linear separable or exact differential equations, so that it could be solved with a set of very specific substitution. Most first order differential equations, however, fail into none of these categories. In fact, even those are separable or exact cannot always be solved for an explicit solution. Without explicit solutions to these, it would be hard to get any information about the solution. So what we do when we are facing such differential equations we can't solve, the answer is Euler's method. If you are only looking for long-term behavior of a solution, like you can always sketch a direction field, and this can be done without too much difficulty for some fairly complex differential equations that we can't solve to get exact solutions. Mainly the problem with this approach is it's only really good for getting general trends in solutions and as well as for long-term behavior of solutions. There are times when we will need something more, like for instance maybe we need to determine okay how a specific solution behaves, even including some values that the solution will take. There are also a fairly large set of differential equations that are not easy to sketch good direction fields. So in these cases we resort to numerical methods that will allow us to approximate solutions to differential equations. There are many different methods that can be used to approximate solutions to a differential equation, and in fact whole class had taught just dealing with the various methods. We are going to look on one of the oldest and easiest to use here. The method was originally devised by Euler's and is called, oddly enough, Euler's method. So let's start with the first general order. That is dy dt is equal to f t comma y t naught is equal to y naught of summation 1 dy dt is equal to f of t comma y t naught is equal to y naught. Let's put some spaces between it. So this is the basically main equation on which we are going to perform the code task, which can be easily understandable for everyone. Let me first clear the equation, in which, let me see whether I have switched on the recording. So if we talk about the equation where f and ty is known as function and the values in the initial condition, and also known as numbers, from the second theorem in the intervals of validity section, we know that if ff and fy are continuous fractions, then there is unique solution to the IVP in some interval surrounding. So let's assume that everything is nice and continuous, so that we know that a solution will in fact exist. So similarly, if we talk about the tangent line, so we have the tangent line y is equal to y naught plus f t naught comma y naught and t minus t naught. So Let's try this with an example, and for an example I'm using PyCharm. You can use any Python environment. So here we are about to start a Python code to find approximation of an ordinary differential equation using Euler's method. So let's start the roller coaster ride of it. So let us consider an equation, actually a differential equation on which our whole code will be dependent upon. That is dy by dx is equal to x plus y plus xy. Okay, moving onwards, starting the code, that is the function x comma y, which returns the value x plus y plus x multiplied by y. So now putting the function for Euler's formula, that is definition Euler x naught y h x term is equal to y, and y is equal to y plus h into function of x0, x0 and y, which rapidly provides x0 is equal to x0 plus h. We'll talk about the approximation value, and for that we have to print an approximation, that is sorry for the inconvenience, basically the P button paused the video. So again I am printing an approximation value. So for that, approximate value at x is equal to comma, we'll put the variable that is x, and just value won't use के लिए we are using variable y, but we make it more good by using a percentage. It becomes like percentage of 6f y. Okay, now moving onwards, we'll put driver code, and for that we have to take some initial values, and for that I am taking x0 is equal to 0 is equal to 1, y0 is equal to 1, and x is equal to 0.025. Moving onwards, now the value of x at which we need an approximation, and for that I am taking x is equal to 0.1. Now we'll put the Eulers. We put the substances for that. There is x naught, comma y naught, comma h, comma x. Now let's run this code and let's see what we have in output. So here we have an output that provides approximate solution at x 0.1 is equal to 1.111673. So at the taken equation, what equation we had considered, that was dy by dx is equal to x plus y plus xy. So at that specific point we are having the result 1.11673 by using Euler's method. So Euler's method is nice method for approximating fairly nice solutions that don't change rapidly. However, not all solutions will be this nicely behaved, as we have done so many methods before, so we can easily be having such things in our hands. There are other approximation methods that do much better job for approximating solutions, but these are not the focus of this method howsoever. So I'll definitely leave it up to you guys whether you guys wanted to go further in this field. If you are interested, it totally depends upon you. Although noticing that didn't have provided actual solution to check the accuracy of the approximation, because I tried generally to find bounds on the error for each method that will tell us how well an approximation should be, and more obediently these error bounds are again not really the focus of this method. So I'll leave this to you, as well as if you are interested in looking into forward. Thank you.